So good afternoon everybody. Today we are entering into a very new topic which is called as linear filtering. Okay, I'm going to use some kind of additional devices. That's the reason why there was some delay. I was just setting up this page. Okay, page. Right. Set up this one. So, in the previous classes we have seen the fundamentals of image capturing. We have seen what is a digital camera, how does a digital camera work, and so on. So today we'll be seeing how to process the captured images. The first thing is about image filtering. So now, what is basically an image? Here we have an image as a function that is being marked from, say, R2 to R. You have a set of real numbers, you have a set of matrices, and you have one function called as f of x, and this f of x is transformed into another function called as g of x. And see, all the points in this image, if you take an image and all these points in this image is marked by a numerical value. Is marked by a numerical value. Is a screen shared? I want you to stop all other business and listen to me, because you will not understand anything in future. You understand? I agree that there are some technical problems, but you have to listen here only. So what is an image function? You start writing. I want absolute silence there. I don't want anybody to talk. Shall I proceed? Image filtering. What is meant by image filtering? In image filtering, what we are doing is that suppose this is the matrix. This is the image which is denoted by f of x comma y. F of x comma y. Now you are doing some kind of operation. This is called as convolution operation. There will be more operations what we'll be seeing one after the other, and you are creating another image, and this is called as a neighborhood of each pixel. These are called neighborhood operations because you are changing the value of one particular pixel here. Suppose here you are taking this 96 and you are changing these values based upon this neighboring values. So filtering is a simplest of all neighborhood operations which will transform your image from one to the other. You are changing, what are the common operations we will see. How an image is getting blurred, how an image is getting sharpened. All these things we will study one by one. This process is called as image filtering. Image filtering can be of two types. One is called as linear filter and the other is called as non-linear filters. Okay. So here neighborhood operation means every pixel is having or is surrounded by a set of neighbors and these neighbors get the values edited. So this is linear filtering and non-linear filtering. You have two types. And whenever there is an operation which is done with respect to the neighborhood pixels, it is a neighborhood operation. So here filtering is a basic and the smallest and the simplest of all operations. I believe that all of you understood what is image filtering. Filtering means any doubts, any queries. You can stop me at any time and ask me any queries. So what is image filtering we have seen? I told you non-linear filtering is also there. Today or in our syllabus we will be focusing mainly on linear filtering. What is linear filtering? One of the simplest versions of filtering. We have two types, two things, one is correlation and the other one is convolution. We learn what is correlation and we learn what is convolution. So linear filtering, what we are doing is that we are replacing each pixel by a linear combination. Weighted sum means something like an average. Okay, weighted sum of its neighbors. And we use something called as kernel. You have an image, you do some kind of processing and you get this output. And that kernel or the mask is called as filter. Now to define what is linear filtering is a type of neighborhood operator where an output pixel is weighted sum of the input pixels in a local window. Define linear filtering, the answer is here. So let us consider an input image f of x comma y. You are doing some kind of transformation. This is convolution. You have another one called as correlation also. Okay. So in this matrix, this image is being transformed with another value called as h of x comma y. Here what you are doing, you are getting the output image g of ij, that is equal to f of ij into h of kl, and you are summing up all the neighboring operators and then you are arriving at a value here called as for this, for example, you got this 92 here. This is the process of linear filtering. In linear filtering, what you are doing is that you are selecting a pixel, you are changing its value. How you are changing its value? You are using another function called as h of x. Okay, and you are getting an output image g of x comma y, which is nothing but f of x comma y, doing something with that and getting an f of x comma y. You are doing something, you are adding or you are deleting or you are doing multiplying something, you keep it this defined as a weighted average. You don't need to know exact operations that will be seen one by one later on, and then you are getting it converted into a output image, and the output image is nothing but g of x comma y. So what are the basic applications for linear filtering? You can blur an image. I'll teach you what is blurring an image. Sharpen the details. You can cut down the edges, attenuate the edges. You can attenuate the edges. Remove noises. And why do we need this? These filters are essential for pre-processing of all kinds of computer images, all kinds of graphics. Okay. See here. Look at this image, image A. Look at this image, image A. A is the original image. B is the blurred image. You have changed, you have made it blurred. You have changed these values, pixel values of each one by taking the weighted average of neighboring pixels, and that is the reason why you are getting a blurred image. The next image, that is C, which you have seen, is sharpened image. I do not know why this is getting disconnected very often. Are you able to see the image now? So A is the original image, B is a blurred image, C is the sharpened image, the opposite of blurred. Okay, blurred images you know already, you might have taken, you might have seen. The opposite of blurred image is more sharpened. You change the values of the pixel somehow or the other and you make it very sharp. And what is D? I'll teach you as we go on. Okay, D we call it as softened image. We do some kind of hexagonal mapping that we'll see what it is. So here we have two types of operations. One is the correlation operation and the other one is the convolution operation. Okay, so at each point of the output image, I think there is some issue with the Wi-Fi. That's the reason why it's not getting connected. So two operations, correlation and convolution. So this image, this one, okay, this G of I comma j is the output image. It is formed by the input f and h. Okay, in that you have two operations that is called as G of x comma y is equal to f of x comma y convolution h of x comma y. So you have an output image which is represented by g of x comma y that is equivalent to f of x comma y and some operation. It could be a convolution operation that is represented by this or this, a correlation operation which is represented by this or this, and a convolution operation which is this. What happens when you do convolution? What happens when you do correlation? We will be seeing the next slides. Have you all written down? So here you have another important term that you need to understand, which is called as impulse response. Okay, simple. When you do convolution of an function f of x comma y with an impulse signal which is denoted by this delta, which is denoted by this delta of I comma j, you get the same kernel itself back. You have two types of impulse response. One would be finite and the other one is infinite. We can come across these points in the coming slides. Next is what is linear shift invariant systems. So linear shift invariant systems, you have different operations you are doing with linear. You are shifting the pixels from one to the other. The first one is called a superposition, shift invariance, and matrix representation. In superposition, what is happening is the output is the sum of two signals of their individual responses. Shift invariance, that means that you shift certain pixels from one point to the other, there is no much change in the behavior. Matrix representation, see, you may get questions based on this. You may get questions based on this. Matrix, you have two operations, what we have been discussing already. One is called as the correlation, the other one is called as the convolution. Another one, linear transformation or filtering operation, is boundary effects and padding. We'll see what is the effect of correlation and convolution on an image. Correlation produces a result that is smaller than the original image, which may not be desirable in most of the applications. See, this question is, or this problem is very easy. You have an image, you have this, consider this to be an image, and you are doing this pixel wise operations on the image based on the neighborhood values. Let us say, for example, let us take this x. What happens to a point here A where the neighbors are beyond or outside the edges of the image? The value of the pixel at A depends upon its neighboring values, right? Here you don't have enough number of neighbors. What you can do? We can do some kind of padding. Padding means you can add, you see, suppose this is the image. Say, let us take some other, let me take a black color. So this, I am going to add or do some kind of padding outside the image so that that image, that pixel A also has some kind of neighbors. So this A is here. Okay. So when you add some neighbors to it, we call it as padding. Clear? So this is the boundary problem. Boundary problem means the images or the pixels at the edge of the images do not have neighbors. So what we are doing is that we are doing some kind of operations to make these images have some kind of borders. Okay, that is called as padding. This is because the neighbors of typical correlation can extend beyond the image boundaries near the edges so that the filtered images may have some kind of boundary effects. So what are these? What are the boundary effects and what is padding? Okay. So common padding modes. One is that you add 0 in the matrix towards all the border images so that you get a neighbor for all the pixels as well as you put a value of 0 for that. Clamp. Clamp means you are repeating the edges with the same pixel indefinitely. The same edges is being added again and again. Wrap image. You know what is wrapping, right? You are condensing the image. So you are doing the same thing. You are putting a, you are folding an image and making it as a loop. Another one is mirror operation. On the other side, you will get the image, right? So how to overcome the border problem? First thing is padding and different types of padding. All these are questions. I want you to continuously make notes without me telling every time to make notes. So these are the common padding modes. So this is what happens when you pad an image. So this first one shows 0, where you are adding 0 pixels to the border. You are wrapping, you are just multiplicating or you are repeating the edges. Clamping, mirror, and these things already you know, but see here, This normalized means you are zero padded image and then divide the resulting image by its alpha value to remove the darkening effect. So the thing that is explained here, an alternative to padding. This is normalized zero. The zero, you are simply adding zero values on the borders. Here what you are doing is that you are dividing the resulting image by its alpha value to reduce the darkening effect. So what is meant by normalized zero in padding? What is a border problem? The edges of the image do not have borders, so filtering is difficult, or any kind of neighborhood operations are difficult for the pixels at the edges of the image. So what we do is that we do some kind of transformation, we change the values, we add zeros, we add some average values, we replicate the image from one point to the other, and so on. So the point is that you have to understand what is a border problem and why do you need to do padding. Another one kind of filtering is separable filtering for increasing the efficiency. Here we have, you can write out, you can make a note of this. See, the process of performing convolution requires k-square operations, which is computationally very complex. Okay, so what we do is that we create the k is the size of the convolution kernel. You know that the matrix with dimension k cross k kernel will require k square operations, which is computationally complex. Let us consider this vertical V and horizontal T. So here we have done separability, or we are making separate filters to reduce the complexity or the computational complexity, making the works parallel. Similarly, you get an image matrix, and when you perform singular value decomposition, okay, what happens? Filtering becomes much more easier, reduces the complexity. So this is the most important or the crux of today's lecture. Some examples of linear filtering. First type is a box filter, where each pixel is replaced by its average of the values of its neighborhood. And I'll show you examples. I'll show you the images in the coming slides to make you understand more about what is box filter. Bilinear or tent filter, Gaussian filter, Sobel operator, corner detection. So here is where the example comes. Okay, so this is a box filtering. When you transform this image into a matrix, when you do this operation towards each pixel of this original image, you get a blurred image. Okay, so we can just continue after you have noted down these points. So these are the examples of linear filtering. You have box filter, bilinear, binomial, Sobel operations, corner detection. Okay. So this examples for each of these K, I have shown you how we have derived at an output image for a box for bilinear, Gaussian, Sobel and corner. I'll show you what kind of images you will have when these operations are done. So first one, we'll be seeing convolution operation, or what is blurring. Okay, you are taking this image so this is an example of linear operations. See, this is another one. I've taken the source from where you perform an operation and the output image is blurred. There's some wait, after the class. So another one, here, the next one, I have shifted this image by 1 pixel. You can see that the image is getting shifted. Okay. This is called as Sobel operation. You will get questions on this. This is called as Sobel. So you may write down what is band pass and steerable filters. Break is band pass and steerable filters. The Sobel and corner operations are simple examples of band pass and oriented filters. Band pass filters are a category of linear filters. Band pass filters are a category of linear filters that attenuate both low and high frequencies, allowing only a specific middle band of spatial frequencies to pass through. They are typically used in early vision to find specific image patterns. They are typically used in early vision to find specific image patterns. Specific image patterns means edges and spots. So we have another type of linear filter called as band pass filters, where both high frequency and low frequencies are being attenuated, removed. Is that clear? Final and the last point. What are recursive and infinite impulse response filters? An infinite impulse response filter is the one, write down the definition of IIR. All these things will be questions in your exams. An infinite impulse response filter is the one where the output depends on the previous filter outputs. We have two types, I told you, the finite impulse response and infinite impulse response. Unlike finite impulse response filters, the response to a single non-zero value can go indefinitely. That means the response can be infinite. That is why it is called as infinite impulse response. Okay. If I could get the connection, I would have explained to you in a much better way. But still. Now, infinite impulse response are used for approximating very large smoothing kernels with minimum computational cost. Okay. So with that, we are concluding lecture number 6, linear filtering. Linear filtering is a very important image transformation or image filtering techniques, wherein you are changing certain aspects of the image by considering the values of its neighborhood functions. Okay. For example, we are using a convolution operation. We are using a convolution operation to blur the image. Okay. You are able to understand, right? Correlation operation to sharpen the image. Sorry, it's the other way around. Correlation operation to blur the image and convolution operation to sharpen the image. So basically, we are converting an image from a real set of real numbers into another set of real numbers, and we are converting this back to the image. What are the different steps being performed is what we have seen today. Okay, in that, one more important point what you have seen is the bordering problem, where the edges do not have neighbors. So we are adding some values, or we are doing some kind of replication or some other different types of functional transformations, so that we get an image in a better way. Is that okay? Is that okay for all of you? Any questions? Any doubts? So thank you all. Thank you for attending the class.